Okay, good morning. Welcome back to day two of KiCon Europe 2024. Really appreciate everyone getting up and at 'em. We have working coffee this morning, so I see a lot of bright eyes, which is good. I want to let you know today, day two, we have two rooms running. We have a workshop room that is behind the display tables as you exit out into the common area. The workshop for this morning, starting at 9, is hand assembly with the pixel pump. So if you're interested in doing some hands-on surface mount soldering and how the pixel pump kind of works with that and does that, you can go over into the workshop that will be running for this morning, and then later on today, the workshops will be they're in the schedule. You can take a look at them. We have a workshop on becoming a KiCad librarian and another workshop on board art. So for those of you who saw Clemens talk yesterday, he will be giving a workshop on some of the ways that you can incorporate some of those techniques that he was displaying into your designs as well. But this morning in this room, I have the great honor of introducing Odin the Nerd. He is an excellent demonstration, is going to give us an introduction into some of his work and his interests here and how that can impact circuit design. Odin was born in the middle of the woods on a hippie commune in Oregon, if I'm getting that correct. And he is, please give a warm welcome to Odin.
Okay, hi everyone. Good morning. I'm not only Odin the Nerd today, I'm also Odin the Sick. My kids gave me a cold, which is okay, I forgive them because they're cute. Yeah, I was gonna propose a drinking game. You guys have to take a shot every time I cough, but I figure we should probably be able to get to other talks, and I'm gonna cough a lot, so sorry in advance. I guess we should just get right to it. Today we're going to talk about encapsulation of expertise. And if you're a hardware person, this might not be a technical term. If you're a software person, you probably know this. Show of hands, who works with software as well as PCBs? Okay, preaching to the choir, most people. For those of you who didn't raise your hands, in software, we have this principle where you try to encapsulate your knowledge into a piece of code such that other people can use your code without having to have all of your knowledge, right? So if you write a library, or if you write a framework, or even if you write functions that your colleague is going to call across translation units or across pieces of code, you are going to present to them some interface which has some rules, and this is going to allow them to use your code without understanding how it works inside, right? And much of the last 30 years of improvement in software development has revolved around encapsulation of expertise, right? You know, back in the mid-90s, you wrote most of your own code. And if you used other people's code, it was probably C, which doesn't encapsulate particularly well. C people are going to kill me for that, but it's true, at least in my opinion. You didn't really have unit tests, so if you started using other people's code, you started encountering other people's bugs that they probably didn't encounter, and so you had to go down into their code and figure out what was wrong, and so you needed all the expertise anyway to be able to use other people's stuff. Right? But over the last 30 years, we've developed a whole culture around encapsulating expertise in software. And this is actually where, if anybody knows me here, they probably know me from my software talks. I was a software guy for a while. But lately, I've been cheating on my software self and doing a lot of open source hardware. And most of the software people don't know that originally, like bad old days when I was starting, I actually started out a hardware person, like back then with, analog circuits and, the dirty stuff, right? And then at some point, stuff got smarter, and I had to start using microcontrollers, which led me to this kind of code. And this is not encapsulating expertise, right? Like, if you go get to a microcontroller assembler project, like, you're going to have to somehow Jedi mind meld with the author of that project, or you're just going to break absolutely everything, right? Because it's not well encapsulated. And back when I was doing microcontroller stuff and my stuff was breaking because, I didn't even have a mind meld with my former self, was mostly the problem. Some of my friends were like, come to the dark side, man. Come to the dark side. And telling me to write code in C for my microcontrollers. That basically just made everything bigger, but still didn't really encapsulate expertise. And so I started playing around with C++ on microcontrollers, which at the time there was no infrastructure for, and so it was like a 10-year rabbit hole. So I went down this rabbit hole pretty far, and there is C++ infrastructure for microcontrollers now. And then I got interrupted by some stuff, and for some reason, I don't know if like chip fabs run on toilet paper or what the problem was, but somehow we couldn't get chips, right? And so I was back to doing hardware, right? So I was redesigning things so that the chips that were in them, so we didn't need to pay horrendous amounts for the chips that were in them. We could replace the chips with chips that we could buy, right? And this kind of brought me back into the hardware world. And since I'd been gone, obviously the hardware world had developed, a strong DevOps culture and unit tests and code reuse and all this kind of stuff, right? Regression testing, that would be awesome in hardware. And it's obviously easy to work from home if you're working on hardware, right? Yeah, okay, I lied, right? So a lot of the things that had been solved in software were still very much not solved in hardware. And there had been some improvements in the hardware world, right? Like PCBs got like 100 times cheaper or something. If I compare, the beginning of my career to even 10 years ago, that's already 100x cheaper. And CAD software was suddenly free. Like I had to hack OrCAD for my first stuff because I couldn't afford it. And now there was something that was way better that didn't continuously crash, and it was free. Thanks, Wayne. And the software world had increased productivity, increased reliability. Almost every metric was similar to the PCB price, right? It was, through the roof, right? How did they get there, though, right? Like, how did the software people do it? Because hardware looked pretty much the same. So the way software got there is encapsulation of expertise, essentially, right? They made everything into libraries, into functions, into classes, into modules. It's all about putting an abstract interface around it so that people don't have to understand the guts, right? They just have to understand the interface. And then as soon as you do that, then you can test against this interface, right? You can share this interface with other people. If you don't write any documentation, that's hard, but well, okay, I don't write any documentation. I'm terrible with that. But anyway, also things like one-touch build systems, right? You you codify the knowledge of how to build it, right? And as soon as that's codified, then other people don't have to understand how to build it, right? And so from a hardware perspective, like those software guys are pretty sexy. Like maybe not this particular one, but yowza, right? So this kind of happened to me for a second time then, right? Like, why? Well, maybe we could just, twiddle a few things and whatever, and that's been a 8-year rabbit hole, right? And it's a good rabbit hole, right? Like it actually led us to start the German version of this conference, and this is kind of why we're all here today, because I fell down this rabbit hole with a few of my friends. And actually, some of the first attempts at sort of generic interfaces and encapsulation of parts of circuits were from friends. This is what we called snippets, which are basically piggyback boards that you could solder onto other boards, and so right? But that didn't quite work because we didn't get the interfaces right. And we already have, for all intents and purposes, some encapsulation of expertise in the hardware space. We call them hats, right? So if I have my Arduino, I can get an Arduino CAN hat, and I don't have to know everything about designing a CAN hardware to use it, right? Then I also have an Arduino CAN hat for Raspberry Pi, and then for Featherwing, and this and that and whatever, right? CAN controller's SPI. Why don't I just have a generic SPI hat, right? Because then I wouldn't have to need many hats. So this was kind of the idea that was kicking around. Why don't we make an interface rather than whatever this microcontroller used at some point? Why don't we make the bus systems that connect between chips on the board, right? And about that same time, I found this connector, which has the pleasant side effect of being free, right? Okay, you pay for a little more PCB space, but that's free, essentially, right? So you don't really have a per connector cost. And then when you actually do want to connect it to something, then you can use these board edge connectors, and you can shove 2 boards from both sides onto that thing, and it connects them. So it's a 10-pin straight through connection that actually works up to pretty high frequencies. And experimenting's good, right? This is not my kid, but my wife would kill me. This is a stock photo, but yeah, I mean the problem with this kind of experimentation is you run into problems, right? So this is a JTAG programmer that uses the same connector as that JTAG programmer, except they have completely different pinning. They don't even agree on what number is where, right? So okay, that's not going to work with the idea of a SPI hat, right? That's not going to work with some universal interface between different components. So why don't we try and standardize them, right? That'll work, right? So we started breaking up a lot of the designs that we already had in house, just as sort of a mental model kind of a thing, and constrained by 10 pins or 20, you can also put 2 of them next to each other if you need it, right? We kind of went through and, well, what should the pins be on different buses? And we also came up with this sort of number scheme. Oh no, I'm crossing the line. I'm not sure if you can read that, but it's basically organization dot interface number dot version, right? The idea being that it can grow beyond our organization, right? Like if you want to standardize your pinning for other connectors, then make your own for prefix. And the OSF ones, that stands for Open Skunk Force, which is our nonprofit philanthropy thing that deals with all our open source stuff. And then we realized, well, actually, there can be a hierarchy, right? It's kind of stupid to make everyone in isolation when they do have a lot of commonalities, right? If you want to power a board, well, you can power it on any connector that has ground in your power pin, whether it's 3.3 volts or 5 volts or whatever, right? So I guess this is not really big enough to read. I'll go through it. Basically, the base node is pin 1 is ground, and the only interface that doesn't adhere to that is Ethernet, because what's ground on Ethernet? Okay, there's shield, but that's still not ground. And then pin 10 is 5 volts. Well, okay, if you're using battery cells, then the battery cell connector doesn't need that, right? And so you can kind of go up the chain all the way up. At the top, you see another generic interface, and this is sort of a generic I/O interface where most of the UART, GPIOs, I2C, whatever. We also standardize like where each which pin is an input and which pin is an output and which pin is bidirectional, so that things like isolators work between there and so on and so forth. And then we chopped up a bunch of circuits and made them into Edgie boards because of the edge connectors. That's why we call them Edgie, right? So up here at the top we have a gigabit switch. Now this is not going to pass EMI compliance in any way, shape, or form, but it does work. And EMI compliance is more of a whole systems thing anyway, so that's kind of outside of the scope of these edge boards. We have a USB hub, we have a CAN transceiver, we have network stuff, DC-DC step-down things work very well. So at this point, we have from these little boards, we have something like 200 of them are open source in the Open Skunk Force project. Maybe 80 of them are finished and tested. Some of them are abandoned. You know how development is, right? You go until you realize the chip's not going to work, and then you abandon it. So it's it's an open source thing, right? But it's documented how far each one is along. And the advantage that we didn't really initially expect was that not only do you have the ability to unit test these things, right? Like you can test it in isolation of the rest of the circuit, but you also have what people in software call a seam, right? A seam in software is basically a place where you can get between two pieces of software to do logging, or more commonly unit testing, or those kinds of things, right? So here is a Raspberry Pi Pico board, the Edgie version, and connected to it we have our LED board, which is super handy. It basically turns the LED on and off depending on the voltage on the 6 generic I/O lines, right? And then behind that, we have a analog digital converter, right? So we can see if it's answering on SPI, for example. Visual debugging is worth its weight in gold sometimes. And then behind that, we have our generic potentiometer board where you can set the voltage on any of the input pins, right? And so we can reuse these development debugging board thingies all over the place because the interfaces are standardized. Oops, close-up shots. Probably should have switched further, right? So we We also were able to make the debug interfaces incredibly cheap because we didn't need any connectors, and there's open source versions anyway, which kind of help. Like if you can get between different interfaces, and you can permanently install a debug interface, and Raspberry Pis are cheap, you can almost debug your hardware remotely, right? Which, I mean, this was more of a thing during social distancing. It's less of a thing now because we like in office for other reasons. But it was quite handy. We also have sort of the concept of a composition of Edgies, right? So here we have the same Raspberry Pi Pico board with a SPI Ethernet board connected onto it. We do a lot of Ethernet stuff. And then we have a power over Ethernet and DC-DC converter board. This is kind of the basis of most of our sensors. We do a lot of physical measurement of critical infrastructure or industrial machines or that kind of thing. Like if you want to do diagnostics on your valuable stuff that needs maintenance. So then one other thing I realized is, well, if you want to do remote work, then you probably want to know what's going over the bus, right? Because a lot of the work of doing the firmware side of things for the firmware guys is actually communicating with all the chips, right? Once you can communicate with it, you're almost done, right? So we can just put another one of those Pico boards in between and run a logic analyzer on it through the internet, at least in theory. Now this is the free version of the logic analyzer. You can buy a very expensive logic analyzer that actually works. But this is me again and again and again, right? So yeah, that logic analyzer, nobody's gotten it working yet. Like it worked for 30 seconds and then it crashed and then it's never worked again. But in theory, like you have to, like this is a essentially a two-man part-time project over the last couple of years. The concept is more powerful than the implementation. We'll put it that way, right? But I can show some sort of success stories. Here we have two products of ours. Here on the left is a small PCB that you can put into a stack light. If you don't know what a stack light is, like on industrial machines, you have like a red, yellow, and blue, and usually some other color, which is probably the color of the logo of the company that made the machine or something. And basically, it's a status status output of whatever the machine status is, and they're usually hardwired, which is stupid because you have to pay people who know where wires go. And with Ethernet, you don't. My kids can plug Ethernet in. And so yeah, it's a power over Ethernet stack light adapter. It's a composition of Edgies, right? So the way our development cycle works, we talk to the customer what they need, right? And usually same day, we sketch up a composition of these Edgie boards, which will result in that product, right? And there's usually going to be a few that we don't have yet, right? But at least we know exactly what's missing and what interfaces it has to fulfill and whatnot, and what we already have. It allows an incredible level of reuse, especially because we make a lot of very similar products, right? We know this from software is composition, right? It's the mix-in pattern, if you will. right? Or I mean, there's other forms of composition. It's the same composition is here. So let's look at this sort of in design. All of the Edgie boards are subsheets, and the order of the connectors kind of falls out automatically because we have an edge connector symbol for each of the standardized interfaces, right? And it has an order of pins. And so if you're lazy, you're going to use the same order on the other side of it, right? And so it generally just works, right? Here's the big board as a composition of edgies. Yeah, and here's the big board is the mermaid graph of all the pieces. So it turns out the big board is a network switch and a Raspberry Pi and power, right? And so, I mean, we actually did have, oh wait, this is outdated. I'm sorry, documentation is out of sync with the hardware. Anyway, so we actually made this design with a different CCPC board than the Raspberry Pi because you couldn't buy the Raspberry Pi, and that used less power. And we were able to just swap out the step down with a more powerful one that we had from another project quite easily. This also works quite well with Git submodules. We pull in each Edgie board as a submodule, and then copy over the subsheet, and it works, right? It's still more manual labor than it should be. That's another part of the project that is not finished yet. There should be some Git extension where you just, git add sub Edgie or whatever the syntax is, and it'll do it for you. But yeah, so that's how we develop hardware at this point. Like it was sort of a test project, and then we realized it actually pulls its weight. And so when we do new designs now, we usually do Edgies first, and then compose them as a second step, testing all the pieces in isolation to begin with. Because, I mean, I don't know if this tracks to your experience, but at least half of my errors are really stupid, right? Like I use the wrong footprint, or I don't know, forget to power all the power pins, or just really stupid stuff like that. And the advantage is, if you do an Edgie first, then you only screwed up a tiny little board, and it's really easy to find your error quickly, right? Because you have the interfaces, and you probably have a whole bunch of other test boards that you can just plug onto there and see within 5 minutes whether the chip communicates over SPI, right? Like you can bring the board up and tack to it using MicroPython before you actually write the code for whatever other processor you're actually using with it, right? Here we've also found a bunch of maybe unexpected advantages. Stefan's been getting very sophisticated in GitHub action chains. So now if we set a version number, then it will run a bunch of tests on it and spit out all of the production files and whatnot. We haven't actually talked JLC PCB into giving us their interface so that I can actually order them, but that is the next logical step, right? The other advantage is when you're doing the Edgie board, like the isolated module, if you put in DigiKey part numbers, or part numbers from someone else, thank you DigiKey for sponsoring, then they bubble up automatically into the top level project, right? Because you imported the whole sheet. right? And so the part numbers come with you, and you are also verified that you didn't use the wrong package size or something, right? So there's a lot of stupid mistakes that you notice early on, and then you can reuse that small piece, basic block of circuit in many, many designs after that without making the same mistakes again, right? So, at top level, you have to reroute everything and, look at EMI concerns, right? Or EMC, right? I guess I already touched on remote work. We're getting there, I guess you could say. One other huge advantage is with the cost of sort of PCB manufacturing at this point, you can basically build throwaway hardware essentially, right? Like this is our basic Raspberry Pi board. I think this costs us like €4 to assembled in quantities of 100. So these are just everywhere as a logic analyzer, a buggy logic analyzer, as some kind of input generator, right? So, MicroPython script on there that just turns a pin on and off in some frequency, or so on and so on, right? So, yeah, it does, it has posed somewhat of a logistical challenge. We're no longer stocking parts, we're stocking Edgie boards, right? And in our warehouse system. It has probably paid for itself at this point. I mean, I think we're well in the black. I mean, it was a pretty big initial effort, but it allows us also to move tasks from senior engineers to junior engineers, which is, if you've been involved in larger operations, that's worth its weight in gold, right? So, whoever designed the Edgie can just, as an issue in its GitHub repository, say, hey, test this, tag some junior dev, and say usually the testing routine is connect this Edgie board to one side, connect that Edgie board to that side, run this MicroPython script, and verify that the output is this, right? Those kinds of tests can be done by someone who's not the expensive guy, right? Who never has time. And can also, because those are hard to schedule, because depends on customs more than anything else, when the board is actually going to arrive. And so, yeah, that can be done asynchronously to whenever the expensive guy has time, right? And you can't really do this with big composition boards, right? With everything on it, because you don't want the new guy to break it, right? But assembled PCBs at this point are dirt cheap from China, right? I mean, it's cost of components plus $2 or something. It's just insane, right? So you get 5 automatically. They can break one, it's fine, right? So that's our experience with this style of development has completely changed how we do PCBs, and almost all of our Edgie components are open source. The organization is Skunk Force on GitHub. Pull request welcome, obviously, and I'm going to open it up for questions.
Hi, thanks for the presentation. I had a question about form factor of the final boards and mechanical.
Yes. Well, we standardized kind of the standard height of an Edgie board is 16 millimeters and width is 24 millimeters, and then multiples of that except on each edge, you have to subtract 1.5 millimeters, which is the space of the plug, right? So that two small ones connected with a plug in between is as wide as one big one. And the reason why we use those dimensions is it lines up with the bump spacing on Legos. So you can actually glue the connectors to Legos and then assemble your circuit on top of a Lego thing, and then it doesn't wiggle. Yeah, but very good question. Anyone else? Don't be shy.
So where do we find this stuff? I mean, I don't find any reference in the presentation notes, or you didn't
yes.
bring anything. And if it's open source, where is it?
GitHub.com/skunkforce, written together. So skunk and then force without any underscore or space or anything.
And again, regarding to the open source, how big is the community around this? How many users externally, or is it only your company, or what's the scale of this?
It's small at this point. I mean, this is the first English language talk I've given about it, and that's kind of the only way people hear about these things. So, yeah, I mean, there are more people using the stuff than contributing. There's maybe, I don't know, 10 people using it outside of our organization and one outside contributor or something like that. Like it's very early days. It's also not super polished, right? I'm also not, I mean, I don't see any big showstoppers in the way that we made it or standardized it. But like from a probability standpoint, there probably will be something better eventually, just because this sort of idea and space is relatively new. What I think is more important than the actual implementation is the idea of encapsulating hardware because boards are cheap now, right? Like, you know, if you want to know why something hasn't been done yet, it's usually because it turns out to be a stupid idea in subtle ways, or something changed recently enabling it, right? Otherwise, someone else will have done it. And so, yeah, the advent of cheaper boards and cheaper assembly and so on and so forth kind of allows this. And so I would expect a bunch of other people to do similar things, and eventually we'll get a really good solution. This is the best I've come up with. Yeah, I think we got a bunch of questions. Where's the mic?
Here. Here.
Oh, yes, there.
Okay, I just didn't get the detail how the pinout is specified or standardized.
Yes, the specification of the pinout is one repository in the Skunkforce organization. There is both our specification of how we specify different pinouts of buses, as well as the sort of naming convention of this is an edgy pinout that uses that fits somewhere in some hierarchy, right? So if you want to add to our specification, you can either do pull requests or you can do it under your organization. There is a guideline of how to specify pin. There's also a guideline of sort of minimal requirements to be an Edgie board, and listed on our list of finished Edgie boards. Yeah, it's all in the Skunkforce repository. Yeah, I mean, like I mentioned in the slide with the text that was very, way too small. We do like the idea of sort of a hierarchy, although that idea came relatively late, and so it's not completely implemented across the whole body of work. But I mean, if you specify your own Edgie interface, it would probably be a good idea to have pin 1 ground as well, so that stuff doesn't burn when we connect the wrong thing to the wrong thing, right? Or to fit somewhere in the hierarchy that's already there, right? Defining some minimal number of pins. Yeah, I mean, so far we have basically all of the interesting digital buses, including the Ethernet controller to Mac to PHY, all the variations of that, or at least all the ones we've used so far. And then, some of the field buses of, on the physical side. Yeah, I mean, that's basically what's been standard so far. But you actually get, and like GPIO, generic GPIO pins and analog input, output, gets you pretty far. I mean, most designs just have that, right?
Oh, yeah.
Yeah, Nick?
First, I want to say, would have been a disappointing drinking game.
Oh, yeah, I got far.
I was wondering, I'm not that experienced in manufacturing, getting PCBs manufactured. Are there special needs for the edge slot connector, or is it the standard process of PCB manufacturing?
Yes and no. There are, the hardest thing to get manufactured is actually the width and tolerance of this notch, which is weird to me because that's like everything else is a tolerance of 100 times the, yeah. This notch is basically set to the specs of our two European PCB producers plus JLC PCB, which is like half the market or something at this point. I believe the American, what are the purple guys called again? Osh Park, yes. I believe they can do this too. There is one other German place that can't, but I think it's because they, Eisler, I think it's because they pool across a whole bunch of different manufacturers, and so the lowest common denominator is what their official spec is. It hasn't been too much of a problem. I know that the original, my original inspiration, the debug board actually is set up a little bit different in from a footprint standpoint to allow a wider milling bit, but that actually leads to problems because the plug can wiggle, which I think led to the demise of people using that. But if you specify it narrow, then it doesn't wiggle so bad, especially if you put it on Legos. And so, yeah, that is a very good question. And I think PCB manufacturers are just going to get better over time, and so it'll be less of a problem. At least one would hope. We also thought about scrapping the whole idea of edge connectors once I saw how cheap USB-C plugs are. You can also get both sides of a USB-C plug PCB mount, so you could just connect everything with USB-C plugs. But those are really hard to hand solder, on the other hand, right? So you'd be kind of tying your fate to pick and place machines. And we do hand solder some of them sometimes. So yeah, I mean, maybe somebody will do that at some point and it'll be a better idea. It would help with the high frequency. Like gigabit Ethernet does actually go through the connector. It's not going to pass compliance or anything if you have. I mean, it's a very good way of testing, how resilient your circuits are to noise. But yeah, if you did the USB-C connector, then you wouldn't have those problems either. That might be a good idea at some point. Yes.
So you have to speak up, and Odin, if you can repeat the question back for the microphone.
Oh, sure. Yeah, no problem.
So you encapsulated by the hardware modules, and on the other hand side, in target, you encapsulated
Yes.
Okay, and
So the question was whether I encapsulated from the hardware standpoint with small circuit boards and in KiCad with subsheets of schematic. And the answer was yes.
and when you finish your tests, you just pack everything together in KiCad, right?
Yes. When I finish all the tests, I put everything together in KiCad, yes.
Yes. And the question is the way you put them together, is it easy, just is it copy and paste, or how do you do it?
The question is whether that's an easy process, and it's not hard. There is a description of exactly how to do it in the repository. That is one point that I think one could use to improve. I mean, ideally, you're already adding the submodule through git add submodule on the command line, and Git is extensible. One should be able to add a custom Git command that would add it directly to the top level sheet in KiCad as well, because the format's open. If you see Tabea running around, I don't think she's here today. She might work on that once she's done with all of her other stuff, because she does know how to do Git extensions. She's one of those people that has an endless backlog, even though she's very good at working it off. Just more stuff comes, so I don't know how soon that's going to be. I mean, ideally, it would be easier, but yeah, basically how you do it is you copy over all of the subsheets, add all of the libraries, copy over all the libraries add all the libraries to your project, and then add sheets with the same name, and then KiCad asks you, well, we have a file of that name, you want to use it? And, yeah, I want to use it, and then, yeah.
The last question about it. So would it be a good suggestion to have, let's say, templates for sub-sheets in KiCad? So I have ready-made schematics. I can use it as models for new schematics, just to something like a template for a project, but a sub-template, a modular, like you did with the hardware?
Yes, we have an Edgie board template. There's a template repository, so if you want to make an Edgie board.
Is your mic still on?
I think it's, well, okay, hot swap. Okay. We do have a template repository for the Edgie boards, as well as an Edgie board project. I forgot to mention this in the talk, which is kind of similar to your question, so I'll put it in here. The way the Edgie boards themselves are structured is you have a subsheet in the Edgie board supersheet, right? So that the sort of basic block doesn't have the edge connectors on it when you import it in the super project, because you take the subsheet out of the one project and put it in as a subsheet in the other project. We also do stuff like extra decoupling caps and EMI stuff and whatever that is specific to the Edgie board that wouldn't be needed on the top level board, or might be needed differently on the top level board as sort of outside, or things like strapping resistors or whatever. You don't want to do that. I mean, you do want to have those components on the Edgie board, but you don't want the same strapping resistors, bubbling up into the top level where, reset doesn't need pull up, it needs actually connected to an output pin in your microcontroller or something, right? So yeah, good question. I didn't explain that well enough in my talk, but so it's a, taking a subsheet out of one project and putting it in another project, because that's the conceptual basic block. More questions? Did I drain the audience?
One more. Could you compare this to the Seed Studio Groove connector? Is there an overlap? Are they complementary?
I am not so familiar with the Seed Studio Groove connector. So I guess I can't comment. But thank you for something to look at later.
So I looked into this and I found it's quite hard to find a 3D model. So there's not one in the internet. Do you have one sketched up and are you willing to contribute it?
3D model of what exactly?
Of the edge connector to stitch it together in CAD.
Yeah, no, we don't have a 3D model of that either.
And the footprint is not in the KiCad library either, right?
We made our own footprint and provide it.
Yeah, it's in the Git repo, but...
Yeah, no way. The one in the Git repo is ours.
Okay. But you might think about contributing it, maybe without the spider, even though it's cool.
Yes. Ours doesn't have the spider because it gets in the way. We actually still use the debug edge connector on our boards when we need a debug edge connector. I guess that project was somewhat abandoned because of the wiggliness, but we didn't know that earlier. But yeah, we figured we should be compatible to people that already have debug stuff, and so the spider is the way you can tell if it's ours or not, right? Yeah, yeah, it's we have contributed. It's in this Skunkforce library. And as far as the 3D model of the connector, we usually just need 3D models of the actual composition, like the board we're going to sell the customer and that has to fit in a case or whatever. We haven't really needed the 3D model for our stuff. I mean, it'd be cool, but yeah, no, huh? Okay, Stefan will make it. Stefan's our 3D model guy. Well, he's one of our 2 3D model guys, but he's the one of the 2 3D model guys that actually produces stuff. No, sorry. More questions?
Yeah, I got the mic over here.
Oh, okay. Back where I can't see because the lights are blinding. Yeah. There we go. I can see you now.
Here we go. You had this picture in your presentation lining up some Edgie boards. I think one was LED, and then you had like a AD converter, and then potentiometer, something like that in there. Exactly that one. So the sequence of the board makes sense, right? There is no. I think you have the controller board, and then so the right one is only analog, and the middle connector is like a digital interface. So do you mark the boards? Is there like
yes?
Like
I'm going to step over this bad guy line here. This number here is the number of the interface spec. Right? Oh, camera followed me. Okay, this number here is the number of the interface spec. So the numbers that where the second section begins with B are boards. If it begins with C, it's a composition, and if it doesn't begin with a letter, then it's an interface spec. Right? So here we have 007, that's analog pins. Here we have 100, that's generic digital IOs. It's the base class of all the I/O stuff. This is another reason why base class is interesting, because here we have SPI, here we have SPI, and here we have the base class, because if it's I squared C, the LEDs work too, right? And so, yeah, out of the hierarchy, you can see what is compatible with what. And next to the connectors, you can see which, like here we have another interface spec. I guess from the picture, it's not really clear that you can see it from the silk screen, but on the actual boards, the silk screen is readable. So yeah, that's the idea. So if you see on a board the interface spec on the left and right are compatible, then you can connect them together.
So there's 2 pins for power supply. These are fixed on all the boards so that I don't break anything. Do you have some decoupling resistors on the other Edgie boards so that in case you put them together, you don't break anything?
Nah. Basically, it you know, if you connect it wrong, it burns. But
Yeah, just to throw them out.
yeah, I mean, so far, everything fits into the hierarchy such that it doesn't burn because the power pins are all the same. I mean, if people continue adding to the spec, then someone's gonna, I don't know, someone's gonna reuse the 3.3 for 2.5 volts or something because they don't use 3.3 in their designs because they do other stuff, and then you could potentially make it burn. But so far, we haven't really had problems with it, but that could be more of a problem in the future. Obviously, you could just make an Edgie board with fuses in it and use that to connect different boards together if you wanted to. Yeah.
Okay, thank you very much, Odin.
Yay.